All right, so I am Ryan Micallef. I am here with Cloudera Fast Forward Labs. We are a research group within Cloudera, and previously on our own just as Fast Forward Labs. We do a series of research reports on current topics, things that have just come up in machine learning. One of our recent topics has been on transfer learning for NLP. So I'm going to share a little bit about what we've learned and hopefully get some explanation of what's out there and give you some ideas for what you can do with it. So right now, I guess here's what we do. Run through, talk about natural language understanding, the problem. We'll talk about transfer learning, how it solves it. And then with each of our reports, we develop a prototype product. It's not a real product, but it's a teaching tool and a learning tool for us. And so I'll talk through some of what we've seen in our prototype building and testing. So NLP, this is the cover of the report. We do their actual printed bound copies from Sway Space, the hipster printing press in Brooklyn. And they're beautiful objects. We like to do them. We actually like to see them printed, and we have them in PDFs, whatever. Transfer learning is a procedure to reuse knowledge, reuse training from a problem in one domain and then apply it to a problem in a different domain. Transfer learning has enabled big leaps with NLP in particular. NLP is a very difficult problem to solve. It does cool things, but it's expensive to deal with. So these are some NLP type problems. Chatbots. This is a combination of spell checking and auto-completion. And this is machine translation, just natural language, one natural language to the other. This is a recent application, or again, another toy, really a teaching tool. And what it does is take a writing prompt and turn out text. So the bold text here was the prompt, and then the rest of this was written by a machine, just automatically. In ML, we talk about tasks, and that is you create a model to perform a task. In this case, the task is continuing to write, so predict next sentences. This is done, the previous speaker talked a little bit about GP2, the transformer model that was released, and that being like so good they had to release the dumbed down version, whatever. It was a cute PR stunt by them, but the model's really good. So this just takes that model, you give it a sentence prompt and it'll do it. This is called talktotransformer.com. If you want to play with it, it's fun. A piece of our report is written by Talk to Transformer, a GP2 model. So NLP gives us a lot of capabilities, and here is why it's difficult. It requires a ton of data, and in this case, it's labeled data. It's a problem that requires a bunch of labeled data to build a good model. And it requires great amounts of compute. So training a neural net, unsurprising to anyone at this point, requires GPUs and lots of them. And then ML experts, because within the realm of machine learning domains, the NLP is not a well-settled one, and it requires a lot of expertise, PhD level people working on the problems to know you're getting it right. So transfer learning, like I said, reuses knowledge. Excuse me. And, oh God. Anyway, reuses knowledge to bring information from one domain to another, make your problems easier. So sentiment analysis, this is the one we worked on. It's a hard problem because you have to decompose this. It's not just about parsing the sentence for grammar, right? This car is a pleasure to drive. Well, okay, cool, positive sentiment, not a complicated one. Hardly a pleasure to drive. Well, now it's a negative sentiment. Car is hardly cheap, pleasure to drive, in the middle. So as usual, sentiment is not quite Boolean. Pillow put me right to sleep, easy. Movie put me right to sleep, bad. So you need a parser with some nuance, or a machine model behind it. Same thing here with banking, it's just different sentiments. Yeah. The old approach, the really old approach to this is called bag of words. Bag of words just does a one-hot vector of words in a sentence, right? And so it just adds them up. It's not, it's trivially simple, and it didn't do much, unsurprisingly. So you get this sort of a problem, right? It comes out, did not enjoy it. Well, that's positive because wonderful and enjoy just add up to, right, fine. So clearly that's not good enough. A while back, something came out called word2vec. That's been pretty popular, so you might have heard of it. And what that does is take a word and project it into, it's encoded into a vector space. And this is sort of a two-dimensional reduction, but essentially what it shows is you've got related words that cluster right up. So you can do things like addition, because each word becomes a vector. It's just a really long vector of probabilities or floats effectively. And so you can add and subtract them. The classic version is was it king minus man plus woman equals queen. And you can do Germany minus Berlin and add France and get Paris. So this was fun, and it actually worked way better. And word vectors itself enabled some advances, but it wasn't enough. Didn't get us where we need to be. So here we go. The word fall. You can encode into a vector fall. It will always encode to the same vector. There are many senses of the word fall. Banking earlier, I want a credit card. I need to do some banking, or I'm banking on that happening. It's not, that nuance is lost in word2vec. So the new thing, the thing we're actually here to talk about, context, contextual token embedding. So I'm just going to run through this quickly. So the tokenizer breaks down language into these individual components. That's usually words, but it can be different granularity. The token embedder is going to pull out the embeddings, like word2vec style embeddings. And then you have the contextual token embedder, way more complicated. But what it's doing is taking into account word order and the senses of the word based on the word's context. So if the word fall appears in the Wikipedia article, it's going to try to learn, and pretty much has, learn what the context is surrounding fall. And this contextual embedder will tell you that there are different contexts for fall or banking. So that's, up to this point, what we have is training a big model. So the prediction is just the last step. And I'll just talk briefly about it. This is the feature on your phone where you are auto-completing text. And the reason we do that as an initial training model is the data is self-labeling. The label is the next word. So if I have a 500-word Wikipedia article, for example, this classic training data, the next word itself is the label for the previous prediction. So if I want to teach a machine to predict the next word, well, go to that article and just take the word that's after it, and that's your label for the previous word. Okay. Now, transfer learning. If I want to learn how to drive an F1 car on a racetrack, I can start from zero with someone who's never driven a car before and teach them how to drive an F1 car. That is clearly a lot of information. Starting from zero, if you've got 16-year-old, 18-year-old with a driver's license, you have a lot of work to do. If you start with someone who's already driven a sedan, or regular, your Honda on a public street, highway, whatever, a lot of that information is similar. And you can do a pretty good job, you can get 90% of the way there or more, having driven a Honda on public roads. And the spirit of transfer learning is to adapt. So we take a known task and we move it to a target task. This is the autocomplete task, next word prediction. This model got it wrong. Chicago pizza is not pizza. This deserves to be corrected. I have feelings about this. My colleague, anyway, point of contention. So this is the source task to target task mapping, right? Coffee here isn't bad. It was actually really, what's the next word? Enjoyable, right? And this is taken from isn't bad, right? Or there's probably more context in here that we don't even understand, but that's what the model's going to come up with. Now, the target task here is the sentiment model. I want to build a classifier that says good or bad. So in this case, coffee here isn't bad. We just get positive. That's it. It's a Boolean output. So what this enables, you don't have to spend a ton of money, get a bunch of labeled data, get a bunch of huge compute, and get a bunch of PhDs to build a model. Somebody else did that for you. Actually, a bunch of somebody's else did that for you. These are now publicly available models. You just take that and you apply it to your problem. It's not trivial, but it's also a fraction of the complexity of what you had to do before with NLP. Excuse me. So we built this prototype called TextFlix. It is a sentiment classifier for Netflix reviews. It's a Netflix data set. It's just what's available. And we basically took a bunch of these and trained up a model, starting with a model called BERT, which some of you have probably heard of. But within the last year or two, a few big players, AllenNLP, which is a University of Washington-based group. Google's done one. OpenAI Initiative has done one. That's the GP2 one. So we took BERT and we applied it to these brief, sometimes longer articles, reviews of movies. What we're doing here, this is what our product actually puts out. Right? TextFlix just says, here's the amount of positive we see here. This one we're a little ambivalent about. We're not too sure. And another thing that we do in the product, here we have Lime. If you have heard of this, it's Lime is an introspection tool, interpretability tool that goes around machine learning models and usually black box models and tells you which of the inputs the output is sensitive to. So in this case, our product TextFlix goes through and tells you which of these sentences matters to the outcome of the machine learning model, which is useful for determining how we got where we did. Right. Classic example. So what are we comparing BERT to when I say this thing is doing well? Naive Bayes support vector machines. So deep learning is the new hotness, of course. Support vector machines are kind of one layer behind that in complexity, which is a lot less complex. And we use this as our baseline for comparison. So in this case, we use a naive Bayes support vector machine. But it is doing essentially the same thing, doing the embeddings. It's not that complicated, summing the embeddings, and then doing a classification at the end. And then this was the BERT picture that we looked at before. If there's anything to take away from this, it's this chart. So naive Bayes performance in blue and BERT's performance in orange. So we did this as a series of tests. We took a BERT model out of the box. We used BERT large, if you know these things. And we just gave it a few more samples to fine tune. So we took the driver who knew how to drive a Honda Accord on public streets, and we just showed him 10 more examples of how to drive an F1 car. And then 100, and then 1,000, and then 10,000. And we just tested the accuracy as we went. Same thing with naive Bayes. We just took a model that was randomly initialized. So keep in mind that our task here is to do sentiment prediction. That's yay or nay. So it's a Boolean output on a kind of non-Boolean problem. So straight out of the box, we see that BERT was doing better. So BERT trained on 10 examples in the target domain, which is sentiment or target analysis, target task, excuse me, of sentiment prediction in the target domain, movie reviews, already gets good from the beginning. And then it very quickly arches up. So the important bit here mainly is how fast you get to reasonable performance. So given that we have a Boolean task, 50% is guessing. You know, naive Bayes until you get to a couple thousand test or training examples doesn't even get useful. So BERT wins at every number of points. And again, importantly over here, why this is highlighted at 100, it's 100 examples you could hand label. That's manageable for a person. That's a day of work. It's a crappy day, but it's a day of work. Just you can do 100 of those things in a day. Okay, so AllenNLP, and that is a framework that's available. It's great, it's convenient. Recommended if you're first dipping your toes into this over PyTorch. So that's the underlying deep learning framework. This is everything AllenNLP took. These are the actual parameters for what we built. It's obviously, there's a few more lines of code. This is cheating a bit. But this is really what is needed to put this thing together, to show, to take BERT from a out-of-the-box model and then fine-tune it for movie review sentiment classification. That's the machine we did it on. That is, we call this machine Toymaker. And it is not a company. It has one GPU. I think that GPU is 4 years old, 3 years old. And Toymaker is not a table. I think there's other stickers on it now. Yeah. So we'll just cut to the tricky bits. So sentiment's not binary. We mentioned this before. This review in total is ambivalent, right? It has opinions on both sides. That's all of us. We contain multitudes. So it's a success in the sense that our model, with BERT, our trained model based on BERT, overcame that duality. It had great performance despite, a bunch of these reviews being, feet on both sides of the movie. Another success, Nuance. So this is, we're comparing BERT to naive Bayes, and each of these here is reporting its probabilities of negative versus positive. And this is a layer of introspection that is telling us what were the reasons for that. So we want to know, for example, naive Bayes, the model was sensitive to sit, and it believed this is a negative review based on the word sit primarily, and could some. And then Romance got it, 41% positive. So, and on the, excuse me, on the BERT side, we're analyzing sentence by sentence, right? This is a contextual model. So, and actually, we're analyzing it more than the sentence level, but for purposes of Lime, for introspection, we are interpreting one sentence at a time. So Lime will subtract this sentence out, see the change in the outputs, add the sentence in, subtract a different sentence out. And so it's analyzed at that level. But it's important to know that the contextual models are doing more than just the sentence. We can't fully understand what they're doing, of course. They're neural nets. So given the way this embedder works, we know that it's looking at the document as a whole and the sentence around it and each word within its context. So we've overcome this nuance here, in this case, negation, right? Valley Girl is or is not one of the few romance films I could sit through. That's a pretty complex thing to say either way, with or without the not. And now, adding the not, it's very clear that the negation has flipped BERT around. BERT is very confident in this case that this is a negative review. And then naive Bayes, 59%. It's, naive Bayes isn't too thrilled either way, so it's kind of still sitting on the line. So this is one of the failures we found out. Sarcasm, of course. And this is, obviously, it's misleading because nuance, it's super nuanced, right? Context matters is, by definition, you are saying the opposite of what you mean. Teach a machine to disambiguate that. So we're not there yet. BERT has not figured out a way to understand that context, but that is for the future. So yeah, to summarize. There are now all these machine learning models out there for natural language processing. They've taken the source task and the source domain of generic text, mostly English, but I believe there are a number of other language models out there and more coming. So that's our source domain, is the entire scope of the language, the natural language English. And the target, or the task rather, is to predict the next word. We've taken that knowledge and moved it over to a set of tasks within a different domain. So in this case, movie reviews and sentiment classification. It can also be spell checking. It can also be next word prediction. It can be translating from one natural language to another. Here it is in English, give it to me in German. So we have all those target tasks in target domains that we can do just by borrowing these models from the source task and the source domain. And because we're reusing all that knowledge, we don't have to show it many more labeled examples, right? We're starting from a driver that knows how to drive a Honda on city streets, and we're just adding the information that we need in addition to that to learn how to drive an F1 car on a racetrack. You get that for free. So now you need less talent. You don't need PhDs to do, well, you can do tasks you would have needed PhDs to do before. You can work with less data. You can take one human's day worth of work and use that reasonably and get decent performance. And you don't need, a fleet of GPU machines running around to do it. So a laptop or a machine with one GPU in it now can do a great job with 10, 100, 500 examples and get you there. So hopefully y'all can run out and do something cool with these models that are available. And that is it.